All right, so this is going to be exam 6, chapter 8, part 2. And we're still going to, we left off talking about the covalent bond model. And there's Desiree.
Kathy said she's going to be a few minutes late. She didn't get off work until late.
Okay. So we left off talking about bond energies. And we had just introduced a topic of a theory pertaining to covalent bonds. We're going to carry that one step further. And with the next slide, we get the localized electron bond model. And this can get kind of complicated, but the localized electron bond model is based upon the valence bond theory. And what the valence bond theory says is that actually the key point here is that the valence bond theory and the model, the localized electron model, says that the electrons belong to the atoms of their origin, and they stay belonging to the atoms of their origin. They're only shared in order to form the bond. But we consider those electrons belonging to the atom of their origin. That's a key point. So it also limits the application, and we're going to see where the problems arise in just a few minutes. So when we talk about a bond formation between two atoms, and if the electrons belong to each of the atoms and they share, then the valence bond theory simply says that those valence electrons, and that only the valence electrons, not the core electrons, just the valence electrons, are in their atomic orbitals. And we know how to write those electronic configurations and identify the valence electrons, which orbitals they are in. Those orbitals, when a bond forms, those orbitals overlap between the two atoms. And they still belong to the individual atoms, but they overlap enough so that they can share electron densities between the two. Okay. What we're dealing with here is a subset of the quantum mechanical model, and it's a statistical approach, a mathematical approach. It's not something that we actually observe. So the theory and the model based upon that theory answer questions that we have about the bonds and the molecules that they form. And if the theory and the model derived from it answer those questions adequately, and they predict certain behaviors, then we have greater and greater confidence in the model. But when the model does not give us a correct prediction for behaviors, when we change conditions, then we're in that situation we talked about last week, where you have those three choices, right? You can modify the theory, you can restrict its use, or you can throw it out and start over again. Right, so that's where we are with up to this point. And we are talking quantum mechanical. right? We spoke about quantum mechanics in terms of individual atoms. And we're trying to extend that model to molecules where we have bonds formed. Okay, let's go to the next slide. Okay. So for this localized electron model, the electrons are either attached to atoms, and these pairs are attached to atoms, usually pairs. I'm going to give you an example. Say ammonia. Ammonia looks something like this with the hydrogen out the back end, hydrogen out here, hydrogen out here. So it forms a triangular base, but it also has a lone pair of electrons that are not part of the bond. The localized electron model says those electrons they either belong to, they're either localized on that atom, or they're in the bond between atoms. They don't occur anywhere else. Right, I mentioned this is a lone pair. Anything in here would be a bonding pair. And remember, whenever you have one line, that's two electrons. Right. Okay. So in chapter 8, we're going to cover on this slide part 1 and part 2. Part 3 we're holding for chapter 9. So that's just to give you a heads up. And we're going to talk about, we're going to extend our understanding of bonding in chapter 9. But for now, we're going to stick with part 1, in which we're going to learn to describe the electronic arrangement, the localized electronic arrangement around atoms in a molecule, using this method developed by G.N. Lewis, often referred to as Lewis structure or Lewis dot structures. And then we're going to take that information and we're going to try to say something about the geometry, the three-dimensional structure of small molecules using a new model, the VSEPR model. Okay, part 3, you can set that aside until chapter 9. All right, so let's talk about the Lewis dot structure. G.N. Lewis wanted a way to describe molecules that was simple, right, and accurate, and he's relying principally upon molecules that are formed with the second and third period, where we don't introduce, at least in the beginning, we don't introduce d orbitals. We're only talking about s orbitals and p orbitals. Remember, when you have an s orbital, you can have a maximum of 2 electrons in it. And if you have a p orbital, you can have a maximum of 6. So that's where we get the octet. So the Lewis structures are based upon the octet concept. Okay. And we arrange those electrons around atoms first, and then when we bring them together to make molecules, what we want to do is establish an octet for each of the atoms in the molecule. Okay. And that last statement is still true. The atoms are trying to attain a noble gas electron configuration. So here's the way. Well, actually, there are 2 rules. For hydrogen, the duet rule is we have to go with the duet rule because there's not room for 8 electrons. So if hydrogen has 2 electrons, right, it's got its own electron. Maybe it's got an electron from somebody else over here. right? So then hydrogen is happy when it looks like helium. In other words, 2 electrons only. Everybody else is trending toward octets. So if you have 2 fluorine atoms, right, they're halogens, they only need 1 electron, add 1 electron, and you get a noble gas configuration. So 1 fluorine donates an electron to the bond, and another fluorine donates an electron to the bond. Now each one appears to itself as if it has an octet, and it looks like a noble gas. Okay. This is a single covalent bond where you have 1 pair shared between the 2. You have a single line, and that represents a bonding pair. Double covalent bonds, of course, we're going to have 2 lines, which means 2 pair or 4 electrons. So carbon has 4 on either side. And if you look at where carbon is in the periodic table, it has 4 electrons. It has 2 s electrons, 2 p electrons. It needs 4 more to look like neon. Right? So if carbon is built like this, 1s2, 2s2, 2p2, right? It has 4 electrons. If we can add 4, then it looks like neon. Okay, that's the concept. And the way it did it here was it got 2 electrons from one oxygen, 2 electrons from the other oxygen, formed the bonds, and now carbon appears to have an octet. And we can say, we can use a similar argument for each of the oxygens. Each oxygen only needs 2 electrons. So it gets 2 from carbon on one side and 2 from carbon on the other side. And that's how you simulate an octet for each of the atoms in a covalent bond. Nitrogen has 3. Nitrogen would be like this. Let's see, is that right? No. Yeah, that's right. So nitrogen needs, no, that's not right. Hold on a second. Let me start over again. Nitrogen has 7 here, so it'd have 1s2, 2s2, 2p, 3, 4, 5, 6, 7. Yeah, that's right. That was right. So nitrogen needs 3 more. It needs 3 more to make its octet. So one nitrogen shares 3, shares its 3. The other one, nitrogen, shares its 3. Now we have three bonds in the middle. 6 electrons, 3 from one side, 3 from the other. And it makes nitrogen look like neon again. All right. It takes a triple bond to do that. Now, we're going to write Lewis dot structures for several atoms. And these are the steps that you take to write the Lewis structure. Actually, this is the Lewis structure instruction for molecules. If we write a Lewis structure for individual atoms, let's do that first. So if we see carbon has 6, so it has 1s2, 2s2, 2p2. We're only interested in those 4 electrons. So to write a Lewis structure for carbon, we say that 1, 2, 3, 4. Right? 2 plus 2 is 4. We have 4 electrons, and we're only representing the valence shell, which is the highest principal quantum number. So nitrogen with 7 would add 1 here. That means nitrogen would be 1, 2, 3, 4, 5. That would be a Lewis structure for nitrogen. And you can do that with any of the atoms in the second and third period, as long as you're only using the valence shell electrons. Now, when we put these atoms together in molecules, we extend what we know. Let's take a simple one like water. We've got H2O. Okay. So how many valence electrons does hydrogen have? It's only got one, right? One electron each. So it's 2 times 1 equals 2 for hydrogen. How about oxygen? Well, oxygen is 8, right? Electrons. It has 1s2, 2s2, 2p4. Right? That's 4 plus 4 is 8. So it has 6 electrons. So there's only 1 6. Let's see. Keep these in order. It's 1 times 6 equals 6. We have 8 electrons, valence electrons, that have to be positioned for this molecule. Right. Let's see, that would be step 2. Okay, so what do we do next? Well, the next thing you have to decide which atom is in the center, which is the central atom. Water's easy. You can't put hydrogen in the center because hydrogen can only make one bond. Right? So if you put hydrogen in there and try to attach oxygen to it, you've used up its bond and there's no room for the other hydrogen on that hydrogen. So oxygen has to be the central. So then you take 2 electrons and 2 electrons and form a single bond with the remaining atoms around the central atom. So that's 2, 4. We have 4 electrons left over. Next thing you do is you start from the outside and work your way in. Positioning electrons. We can't put any more around hydrogen. It already has its duet. Right? If you count that bond as 2 electrons, then hydrogen acts as if it has 2 electrons. They're in the bond, but it likes it has 2 electrons here. Right? 2 electrons there. So we can't put any more electrons around hydrogen. We have to put them around oxygen. And we have 4 electrons around oxygen. So we say 1, 2, 3, 4. Okay? So now we've used up all of our electrons. And you can recount them. Say 2, 4, 6, 8. 8 electrons in that molecule for the valence shells. All right. So now we have, we check to see, we have a duet here, a duet here. We have 2, 4, 6, 8. We have an octet for oxygen. All right. That's a valid Lewis dot structure for water. Okay. And I didn't look ahead, but here it is again on the slides. You add up all your valence electrons for the molecule. Right. Then you use single bonds to attach atoms to the central atom. And then you continue positioning electrons from the outside in until all your electrons are used up. We can't establish this. Water was easy. It made an octet very easy, very quick. Sometimes we have to add another step, and I'll show you one of those in a minute, to making an octet. Let's do PBr3. And remember, if you use the Roman numeral group numbers on your periodic table, then if they're 1A, 2A, 3A, 4A, 5A, if they're the A's, then those Roman numerals will tell you how many valence electrons are attached to that atom. Otherwise, you can count from left to right. PBr3. Okay. So how many valence electrons for phosphorus? We look at our periodic table. We find that phosphorus is in position number 5, it has 5 valence electrons. That's 5 there. Bromine is a halogen. It has 7 valence electrons. So 3 times 7 is 21. We have 26 valence electrons. Okay. Now, this was fairly simple to decide which one is the central atom, which would be phosphorus. But usually, if you have a question about which one, the least electronegative would be your central atom. So you look to the left, right? Bromine's over here, phosphorus is to the left and down 1. Phosphorus would be your central based upon that logic. So we put phosphorus there, we put it like that, Br, Br, Br. So we have 2, 4, 6 electrons have been used to make those bonds. So we say -6, we have 20 electrons left. Now we work from the outside in, making octets as we go. So we have 20. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And so that's, we positioned what? 2, 4, 6 times 3 is 18, right? 18. So we have 2 electrons left. The only place they can go, since we already have octets here, right? 2, 4, 6, 8, then the other 2 have to go on the central atom. And that would be 2, 4, 6, 8. Now, phosphorus has an octet. Everybody's got an octet. That would be a valid Lewis dot structure for phosphorus tribromide. Well, there's water. There's phosphorus tribromide, HCN. Right? If HCN is a gas, that's hydrogen cyanide. And what would it be if we dissolve it in water? It'd be hydrocyanic acid. But for our purposes here, we're only interested in the formula. So we have 1 valence electron there. We have 4 for carbon. We have 5 for nitrogen. Right? Just look at your periodic table, count from left to right, how many positions over, those are your valence electrons. So we add these together and we have 10. 10 valence electrons. Okay. Hydrogen is never a central atom because it only has 1 electron. Right? So you don't have to worry about that. We have to decide which one is carbon or nitrogen is central. Well, carbon is to the left of nitrogen, which means it's the least electronegative. It goes in the center. So we put carbon in the middle, we put hydrogen here, and we put nitrogen there. So that's 2, 4, -4 electrons. 6 electrons left over. So where do we go with our 6 electrons? We work from the outside in. Hydrogen's already got its duet. So we put our 6 electrons here. Okay. Now, that's not a Lewis dot structure because we don't have an octet for carbon. We got an octet for nitrogen. So how are we going to get an octet for carbon without sacrificing the octet for nitrogen? The way is to make more bonds. So we take these 2 here, make another bond. These 2, make another bond. So now we have 3 bonds. 1, 2, 3. These electrons are now in bonds. And we have that lone pair left over. Now we have an octet, 2, 4, 6, 8, 2, 4, 6, 8, 2. That's a valid Lewis dot structure for hydrogen cyanide. Okay? All right. What that illustrates is a more accurate description of the structure of water. We haven't got to that point yet. So let's hold that for now. Lewis dot structures for each one of these. I'm going to have to move over these pretty quick because I'm going to run out of time, and I don't want to do that today because I have a student coming at 2:30. So let me pick one. I showed you ammonia earlier, but I didn't show you how I got there. All right, so let's do ammonia. NH3. Okay, so we have 3 electrons for hydrogens. 3 times 1 is 3. Nitrogen is 5. So we have 8 electrons. Nitrogen has to be in the middle because hydrogen can never be in the middle. Right? So there we have hydrogen, 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 2, 4, 6. All right, so now we have 2 electrons have to be positioned, so we got to put them on the central. Right. So there's your Lewis dot structure for ammonia. Duet, 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 2, 4, 6, 8 octet for nitrogen. Okay. Now for exceptions. The first exception is a situation where we know this compound exists, boron trihydride, right? It does exist. So we've got to explain it in terms of our theory or our model. Well, if we take boron trihydride, boron is in 3rd position from the left, right? It only has 3 valence electrons. And 3 times 1 is 3 here, so we have 6 electrons. Well, let's make 3 hydrogens, right? 2, 4, 6. We've used up all our electrons. We know that that molecule exists, but we can't draw an octet because we don't have enough electrons. This is a case where the central atom is octet deficient. It's an incomplete octet. Now, I'm sure there are explanations for it, but that's beyond us right now. Just recognize that some compounds don't fit the model. We can still draw the Lewis structures, but sometimes we have to settle for not enough electrons or too many electrons. I'm going to show you that one next. So we'll take one of these. Let's say sulfur. Yeah, sulfur tetrafluoride. Okay. Sulfur is in oxygen's group, so it has 6 electrons. Each fluorine has 7. It's a halogen, so 4 times 7 is 28. So we have 34 electrons. Sulfur is to the left. It has a lower electronegativity than fluorine, so it's going to be in the center. 1, 2, 3, 4. Okay. 2, 4, 6, 8. So we've used up 8, and that means 26 electrons, correct? All right. If we make an octet for fluorine, for each one of these, that would be 2, 4, 6 more used up. Well, 4 times 6 is 24, right? So if we do the same thing for each fluorine and complete the octet for the fluorines, right? 2, 4, 6, 8. Then we have 4 times 6 is 24. We got 2 electrons left over, but sulfur's already got an octet. But we got to put those electrons in there because they do exist. So now sulfur's octet, it exceeds the octet. Now the explanation for this one is at our level, fairly simple. Look where sulfur is. Sulfur is in the third period. Right? Sulfur's in the third period. It has 16. Right? So it can be 1s2, 2s2, 2p6, 3s2. Let's see, 2, 4, 6, that's 12, 4 more. And we have 3s, 3s2, 3p4, 2, 4, 6, 12, 16. Okay. What other orbitals do we know that exist for principal quantum number 3? We know that principal quantum number 3 also has a d orbital, right? At very close to the same energy levels as these two. They're a little bit different, but not too far, right? So those extra 2 electrons, based upon our localized electron model, right? All electrons belong to each atom. That's where they go. The lone pair goes into the d orbital. All right. Arsenic pentabromide is a similar situation, only in this case, all the electrons are in bonding pairs. So we have actually 5 bonds around arsenic. But it's still the same concept. You exceed the octet because you have an available d orbital. Like arsenic is in the 4th period, so it actually has 4d as its d orbital. It's able to use the 4d orbital. All right. So we drew this one before. Whoop, no, we didn't draw it. We drew boron trihydride. This is boron trifluoride. And in this case, we are able to complete the octet because fluorine has lone pair electrons that we can use to make a double bond. So we don't have to accept a non-octet for boron trifluoride. Phosphorus pentachloride exceeds the octet. And all you have to do is add up all the electrons before you put them together, and then build your Lewis structure, and you'll see that that's correct. And then sulfur hexafluoride goes way past the octet. It's got 4 extra electrons in the bonds with sulfur and fluorine that have to go into d orbitals. So we're making use of d orbitals here to exceed the octet. Okay. Just observations. Carbon, nitrogen, oxygen, and fluorine are in the 2nd period. They always obey the octet rule. Boron and beryllium are to the left of carbon, and they very often do not make an octet. Not always, but sometimes they do, are deficient in the octet. 2nd row elements never exceed the octet. Sometimes they're deficient, but they never exceed. 3rd row elements, they're heavier, they have access to d orbitals, they often exceed the octet. And we have to say that because those compounds exist. We know they're there. So we've got to modify our theory to explain them. Okay. First thing you do is satisfy the octet rule. And then if you've got any leftover electrons, they have to go on as you move from outside in They have to go on the central atom usually. All right, here's another problem. First of all, nitrate is a polyatomic ion, and you can draw Lewis dot structures for polyatomics. But we've only shown you Lewis dot structures that had single possibilities. There were no other possibilities. But in this case, where we have, actually, I did show you one. Right? That one. That's one possibility for a Lewis dot structure. If we move that double bond around to this one, then that's a different Lewis dot structure. Or if we put it on this one, it's a different one. So this is a similar situation to the nitrate. And we could also draw them like this. Okay, just like that. And then we could draw another one if we put the double bond on this fluorine. Okay, so this is one of the Achilles heels for the localized electron model of the valence bond theory. Because you can draw Lewis dot structures. These are all valid structures. So which one is correct? The theory doesn't let us decide which one is the correct one. So essentially, they're all correct. So Linus Pauling in 1928 proposed the concept of resonance. What he said was, if we're stuck with this theory, then this is one way to get out of it. In other words, these are valid structures, and what they're doing is they're resonating. So they're all right. We don't know which one is right at any one split second. They're just a conglomeration, right? And the reason we can't say, we can't draw a single structure for this is because the model doesn't allow it. The example here in that slide is with nitrate. Nitrate ion, NO3 minus, is a similar situation. Notice that in this case, we must, when we draw the structure, we have to keep the charge. So we drew brackets around NO3, Lewis dot structure, and put a negative there. If you don't put that negative there, then the number of electrons don't add up, right? If you have NO3 minus, then you got nitrogen with 5, you got 3 times 6 or 18 with oxygen, and then you got another one here. Right? So that's 24 electrons. If you don't count that charge, then you're not going to have the right number of electrons. And then we draw the structure. And that's the structure you get with the double bond switching around among those 3 oxygens. That's resonance. They resonate. Sometimes we'll draw it like this. Let's take this one, for example. If we have boron and then the fluorines, sometimes we'll do like that. But that's not valid for the theory. That's just I don't know. It's not kosher. But what this does illustrate is that each one of those bonds, oxygen to nitrogen, they're exactly the same bond length. They're exactly the same bond strength. So that means, remember what we said about double bonds and single bonds and triple bonds. The double bond is stronger and shorter than the single, and the triple is shorter and stronger than the double. Well, if that were the case, then this would be a lopsided molecule. In other words, the bond distance between the oxygen and the nitrogen for the double bond would be shorter, but it's not. They're all exactly the same length bonds, exactly the same strength. So resonance for this model is the only way to go. And this is just one way to show that they're all equal, but it doesn't fit the model. That's the problem. Okay. What we're saying is that with this resonating structure, the electrons are delocalized. In other words, they're actually spread over those three bonds. They can move around the molecule. And that was the implication with resonance. In other words, they're not stuck there until they move to the next one. They're actually a composite of all three. That's a better understanding of resonance than the flip-flopping. They don't flip-flop. Those electrons are stable, delocalized around the whole molecule. And because the model says that we have to draw these bonds the way they are, then this is the only way around it. This is the only way for us to show that this model has delocalized electrons, because each one of these structures is valid and we're resonating. All right. If we draw the Lewis dot structures for each one of these, I don't have them drawn out, but in the interest of time, I've got to skip over this one. Just remember that when you have a charge, you have to take that charge as one electron, or if it's a 2-, 2 electrons, so forth, right? If it's a positive charge, then you have to subtract an electron from your total, right? For example, if we drew the ammonium ion, right? This would have 5 for nitrogen and 4 for hydrogen, -1 for that charge, right? And that would be 8 electrons. So you position 8 electrons in their proper place to make that molecule. All right. So sometimes we have different possible Lewis dot structures for a molecule, and they are radically different from one another. They don't have that simple double bond moving around. In that case, then you need to decide which one is the valid one. And what we do is we invoke a method called formal charge. Formal charge is something of a misnomer. It's not really a charge, but we assign a charge as a way of bookkeeping where the electrons are and how they affect the electron distribution in the molecule. So what we're looking for is, once we calculate the formal charge for each one of the atoms in our structure, we compare structures. And the one that has the lowest formal charge for all of its atoms is the preferred one. Now what we need to do is give you the method for calculating the formal charge. So we're trending towards 0. We try to have a 0 formal charge whenever possible. It's not always possible, but that's where we're headed. And we're interested in only the valence electrons and the electrons, lone pair electrons and bonding electrons. So those are the numbers that have to go into the calculation. So here's the calculation. We take, for each of the atoms in the molecule, let's take an example. Water would be really simple. Okay. So if that's a Lewis dot structure, and this one's easy because there's no other possibility but we can use this to calculate the formal charge. So we take the number of valence electrons on the free atom. The number of valence electrons on the free atom here is 1. Okay. Then we subtract the number of valence electrons assigned to the atom in the molecule. It has no extra ones. Right? So we don't have to subtract anything, but when there's a bond, the bond says if it's a single bond, then one electron goes one way, one goes the other. So we have one electron here, right? And that's 0. Okay. We have 1 minus 1 here, and that's 0. Oxygen's a little different. How many valence electrons on the free oxygen atom? There are 6, right? Yeah, 6 valence electrons for oxygen, right? How many electrons are assigned to it in the molecule? Well, the lone pairs belong to oxygen. So we have 2, 4, and then we have 1 from this side and 1 from that side, minus 2. That's 0. Right? So this is good. 0, 0, 0. Formal charge for each one of the atoms. That's perfect. All right. Let me see if I'm missing anybody. Kathy showed up. And let me see. There's no Zoe. I wonder if Zoe's sick. A lot of my students have been sick lately. Okay, so just to reiterate, the lone pairs belong to that atom. Those are the ones, though we subtract all of the lone pairs. The electrons in the bonds are shared. So hydrogen gets one of them, oxygen gets the other one. If there's a double bond, then you're sharing 2 pairs, or 1 electron plus 1 electron goes this way, 1 electron plus 1 electron goes this way. That's how you calculate formal charge. Let's see, that's just rules that were already given. So let's calculate the formal charge for this one. POCl3. All right, I think it's animated, so let me just go ahead. Yeah, for the phosphorus, the free atom phosphorus has 5 electrons. How many are assigned to it in the molecule? Well, it has an octet, right? So it gets half of those single bonds. It's got 4 single bonds with 2 pair each. So 1 electron from each bond belongs to phosphorus. That's 4 electrons. 5 minus 4 is plus 1. So phosphorus has a plus 1 formal charge. How about there you go. How about the oxygen? Well, oxygen has 6 as a free atom. And how many is it assigned? Well, it has 2, 4, 6 lone pairs plus 1 from the bond. So that's 7. 6 minus 7 is minus 1. All the chlorines, they have 7 electrons, valence electrons as free atoms, and each one has 7 electrons assigned to it in the molecule. It has 6 lone pair electrons and 1 from the bond. So that's 7. 7 minus 7 is 0. So we have calculated the formal charge for each of the atoms in that molecule. And we can't conceive of any other possible structures. Right? Not in this case. That's the only valid Lewis dot structure that we can come up with. We can't develop any others. Well, I guess we could, but it wouldn't satisfy the octet. It would exceed the octet, or it would diminish the octet, and we're not going there. So this one is just calculating the formal charge for each atom in this valid structure. This is another rule. if you add up all the formal charges, then the sum must be equal to the charge on the molecule. If there's no charge, then they have to add to 0. If there is a charge like nitrate, then all the formal charges of nitrate would have to add up to -1. Okay. All right. Here's an example of non-equivalent Lewis dot structures for carbon dioxide. If we drew the carbon dioxide the way we normally would, it would be the one on the right with 2 double bonds attaching carbon to the oxygens. But we could also make an octet with the left-hand structure with a triple bond to one oxygen and a single bond to the other oxygen. And notice we still have our octet, and we've not added or subtracted any electrons. We've used the same number of electrons. So which one is the correct one? Well, if we calculate the formal charge for each one, we find that the 2 double bonds is preferred. Let's do the other one just to prove it. This one, there, and that one. Okay. Carbon's going to be the same for both of them because it's got 1, 2, 3, 4. It's got 4 minus 4 is 0. 4 valence electrons, free atom, minus 4 here. But the oxygens are going to be different. Oxygen has 6 as a free atom, 6 as a free atom. But here we have 2, 4, 6, 7. That's a -1. This one has 6 minus 1, 2, 3, 4, 5. And that's a +1. If we do carbon dioxide, like that one, then now we have like this, and we have 6 minus 1, 2, 3, 4, 5, 6 equals 0. Both sides. That's preferred. Both the oxygens are zeros rather than a -1 here and +1 there. So that's why we prefer the carbon with 2 double bonds, one on either side. Just a reminder, these formal charges are not real charges. They're only bookkeeping scheme. The slide says estimates. Actually, they're not even that. They don't have a charge. But they give us an idea of how the electrons are distributed in the compound. And this way, they're lopsided, -1, +1. Right? This way, they're evenly distributed. That is a much more stable situation. But always be cautious. That's what the beware talks about. Lewis dot structures using formal charges can lead you in the wrong direction. It's not often, but it can happen. So just be cautious. All right. Now we're going to use the Lewis dot structures and rules for the VSEPR model. All right, this is valence, shell, electron, pair, repulsion. VSEPR stands for valence shell, electron pair, repulsion. The central idea for this method is that when you draw that structure for a molecule, and we're going to keep them simple, the electrons in the bonds and then the lone pairs are all the same charge. So they're pushing against each other. They want to get as far apart from each other as possible within the constraints of the molecule. Right? So they position themselves in usually regular geometric structures so that they can be as far apart as possible. That's the main concept behind the VSEPR model. And it's a method, it's a model for predicting the three-dimensional structure of molecules around a central atom. Okay, that idea can be extended to larger molecules. So you can have a central atom with but its attachments, its atoms or groups, and it will have a certain structure. And then you can move to another part of the molecule, it may have a different geometry. So we're going to start off simple, right? Use simple molecules with only one central atom to begin with. What we're trying to do is minimize the electron pair repulsions. All right. Okay. A linear structure will give you a certain bond angle. When we talk about bond angles, you need a central atom, and then you need two other bonds to form an angle, right? If we have oxygen and hydrogen on either side, then the bond angle is going to be here to here to here. And the oxygen would occupy the apex of the angle, right? Whenever you draw an angle, right, you have an apex here, and then you have these two rays going off this way. And the angle is right there, okay? So in our case, these would be bonds. And these would be atoms. And this would be an atom. So there you have your angle. Atom, atom, atom gives you an angle. That's what we're talking about. That's one possibility. That's a linear structure where the bond angle is 180 degrees. In other words, this atom would be over here, this atom would be over here. And if it were like that, if we had this one like that, the bond angle will be 180 degrees. It's just that simple. So we're looking at regular geometric structures. Okay. Trigonal planar is a situation where you have three bonds to a central atom. Actually, you have three electron pairs to the central atom. Right, so you can have something like, this one. Like that, boron trihydride. Right? That would be a trigonal planar. In other words, you can imagine an equilateral triangle being traced out by the atoms with the central atom in the middle of that triangle. Right? So this would be a trigonal planar, and they're all in the same plane. Right? 1, 2, 3, like that. Now, what's the bond angle? Well, if we were just to draw an isosceles triangle, of course, the bond angle would be 60 degrees. Because in a triangle, 60, 60, 60 is 180 degrees inside the triangle. But bond angles are based upon this central atom. So we're looking at that. What's that central? Right? And we know that when you go completely around, right? If you have a compass here, north is there, right? You go all the way around here, that's 360 degrees, correct? So what's a third of 360? It's 120 degrees. So the bond angle for trigonal planar is 120 degrees. Now it gets a little more complicated when you have four groups. A good example of that one is methane. Carbon and 4 hydrogens. And you would have this, hydrogen, 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 hydrogen. That's a Lewis dot structure. You know, do it. 2, 4, 6, 8 octet. Okay. When you have that arrangement, then the ideal structure for 4 attachments to the central atom is a tetrahedron, right? A pyramid with a triangular base, that's a tetrahedron. And we typically draw it like this. It would be like, let's see, there's your base, and then you would have something up here. Hydrogen up here, attached to the carbon in the middle. Let's see, let's put it off center a little bit. And draw it again. Let's say like this. Carbon in the middle, you have a hydrogen up here, and then you have a hydrogen here on each one of the positions of the base triangle. So when you draw the structure, it looks like a tetrahedron. Well, what's the angle here? Well, you got an angle here like that, because these are the bonds. Those are the bonds. That's a bond there. This is a bond here. So the angle is 109.5 degrees. You just have to memorize that one. I don't have an easy way to describe that one. All right. There are several more, and we'll get to them eventually. So, how do we use the VSEPR model? All right. I knew I was going to run out of time. Let me see. Where are we at? Okay. All right. How do we use the VSEPR model? First thing you do is draw the Lewis structure. Confirm that you have a valid Lewis dot structure. Okay. Then you count the number of groups. The name says pair repulsion, which is true, but for our purposes, we're only interested in the number of groups around the central atom. And then arrange them in the regular geometric structure. Now, first thing you're going to have to do is count all of the possible groups around the atom. That includes lone pairs. So, for example, if we had ammonia, right, and we drew it like this, like this, like this, like this, like that, that would be 1, 2, 3, 4. You would have 4 groups. In this case, pairs, right? But not always. So 4 groups. If you have 4 groups regularly arranged around the central atom, that means you've got a tetrahedron. So we would draw the base like this and put the hydrogens here and the nitrogen in the middle, and then up here would be our lone pair, right? And it would form the regular geometric structure of a tetrahedron. That's the electronic structure. Okay. And then if you want to find out the geometric configuration of only the atoms in the molecule, then you don't care about the lone pairs. Then you would just cover up that one and say, what do you got left? Well, in this case, nitrogen is not down here in the triangle, it's up in the middle of the tetrahedron. So what you're looking at is a nitrogen here, and then a hydrogen in the back, and a hydrogen here, and a hydrogen here, forming that triangle base. And what you would have there is a trigonal pyramid, right? Because we're not interested in the lone pair, we only want the molecule. Okay. All right. So let's see, these are some examples. If we do the HCN, we get a linear molecule with 180 degrees. Right? That one's easy. pH3 gives us a trigonal pyramid like ammonia. And the reason for that is this molecule has, nitrogen, phosphorus. This one has hydrogen in the back, hydrogen here, like that, and like this on the base, and then it has a lone pair up there. Right? So it has a trigonal based pyramid, not a tetrahedron. The tetrahedron is the electronic structure. So the trigonal pyramid gives you nominally 109.5 degree bond angle. So the bond angle will be like from here to here to here, like that. What modifies that angle is this lone pair. When you have lone pairs in a molecule, they're not bound by the other atom. They're not constrained within the bond. So they can go, they balloon out like that. So balloon out like that, it puts pressure on these and decreases the angle from 109.5 to 107 degrees. But nominally, tetrahedrons have 109.5 degrees, and that's where you start. And then sulfur tetrafluoride is a seesaw, right? If we drew the sulfur tetrafluoride, we would get, well, I'm going to skip that one for now because seesaw doesn't make any sense to you. What we need to do is look at all the possibilities. Let's skip those for now. What we're trying to do is based upon last lecture that we had, is when you want to know the polarity of the molecule, you need to know two things, correct? You need to know, are the bonds polar? And if they are, then what's the shape of the molecule? The shape of the molecule then will tell you whether those polar bonds will net a polar molecule or they'll cancel each other out and give you a nonpolar molecule. All right, so that's what we're after here. Molecule that has polar bonds will always be polar, not necessarily. If the bonds are all polar in such a way that they cancel each other out, then you have a nonpolar molecule. All right. Let's see. Let me check my hard copy because it looks like I'm missing something here. Oh, it's coming up. Actually, what's coming up I should have done that before we got to this one. Let's skip this one for now. And let's go to all the possibilities for electronic structures and then molecular structures. So in this column, this is going to be a table. In this column, we have electron groups. Right, so we have 2, 3, 4, 5, and 6. That's where we're going to stop. You can go higher than that, but we're not going to. Then we have electron configuration. Actually, that's not right. Electronic configuration is something else. Electronic geometry. Okay. And then molecular geometry. So this is where we're headed, but we have to go through electronic geometry in order to determine molecular geometry. All right. If you have two groups, the only possibility is linear. Right. Let's see. Yeah. Linear electronic geometry. Now, if you've got atoms on both ends, like our example there, right, with the black in the middle and the reds on the end, if you have two groups, then linear, it's linear. But if you only have one bond and one pair on the other side, then it's still linear. Right? So this is the only possibility. Example, carbon dioxide. Right. Okay. I was trying to think of another example where we only have two atoms together. I can't think of a good one right offhand. Okay, if we have three electronic groups, then we have the geometry is the electronic geometry is trigonal planar. And of course, if all of those positions, trigonal planar, if they're occupied by atoms, then this geometry is also trigonal planar. But if we have one lone pair, right, then what do you have? You have a bent molecule, or some textbooks call it angular, right? If you cover up one of those groups, if say you have like this, and a central atom, and then you have a couple over here like that, and you cover that up, you have a bent molecule, right? So one lone pair means bent. Two lone pairs equals linear, right? If this turns out to be a lone pair and a lone pair, then that's the only possibility. It's a linear molecule. Four lone pairs. The electronic geometry is going to be tetrahedral. And of course, if all the positions are occupied by atoms, this is also tetrahedral. If you have one lone pair, right, then with a tetrahedral, one lone pair means that now you have a trigonal pyramid. Let's see, I was given examples, wasn't I? This would be ammonia. We did that one already. This pure tetrahedron would be, say, methane. This trigonal planar would be something like boron trihydride. One lone pair. I can't come up with a good one right now. If we have five groups surrounding that central atom, now we have the best arrangement is to put the central atom in the middle and then put three of them in a triangle here. 1, 2, 3, and then put one down here and one up here. Now, some of those might be lone pairs, but if they're all occupied with atoms, of course, you're going to have a trigonal bipyramid. Okay. Let's see. We're on the next slide. There we go. Trigonal bipyramid. Now, if one of those positions is a lone pair, where does the lone pair go? Well, as it turns out, and this is determined by experimental evidence, the lone pair, rather than being above or below, is actually on the trigonal part. Right. So one lone pair, if we have one lone pair and it's right here, say, what do you got? Well, you got this straight and you got this angle. And if you turn it on its side, you got a seesaw. If you have two lone pairs, then both of those lone pairs are going to be on the triangle. And now you have a T-shape. If you have three lone pairs, now you're back to linear. Right, because they're all on the triangle, on the trigonal part, and you got a straight molecule now. Okay. There'll be some examples of these later. If you have six, now what you've got is, rather than a triangle in the middle, you've got a square in the middle. And that has a special name. It's called octahedron. Octahedron means eight surfaces. Right? And if you draw a surface on the top, you get 1, 2, 3, 4. And on the bottom, 4 more. That's 8 surfaces. So octahedral is our starting point for 6. All right. Now, in this case, when you have one lone pair, it does occupy one of the apexes, top or bottom. So one lone pair now is a square pyramid, right? Just like the pyramids of Egypt, the Giza plateau. You have a square base and the rest of it's pyramid. So it's a square pyramid is the molecular geometry. If you have two lone pairs, then they occupy both apexes, and now you have a square planar molecule. Okay. I guess if you have three, then now you have a T-shape, right? Because three lone pairs would occupy this place, and one of these places, and that leaves a T-shape. Right, so three lone pairs is T-shape. Right. Four lone pairs. Let's see, 1, 2. Actually, when you get to four lone pairs, I think they occupy the square and you have a linear molecule. Don't hold me to that. We need to see an example to prove it, though. All right. So here are examples for the tetrahedron. Right? The transition from the electronic geometry to the molecular geometry. So in each case, we start off with all positions occupied by atoms as tetrahedron, obviously. We're missing one, that's a trigonal pyramid. And missing two, that's a V-shape or bent or angular. If we have the trigonal bipyramid, and we're missing one, that's a seesaw. We're missing two, it's a T-shape. Missing three, it's a linear. So I got that one right. I'm not sure about the octahedron if we're going to show that one. No, it doesn't show an octahedron. Okay. It may be in your book, but I thought I'd put it together in a table like this so you could see all the possibilities. All right. I'm over already, so if you have to go, go ahead. I'm going to try to finish before my appointment. Let's see. How much more do I have here? Just a few slides. All right. In this example, when phosphorus reacts with chlorine gas, the compound phosphorus pentachloride is formed. In the gaseous and liquid states, this substance consists of PCl5 molecules, but in the solid state, it splits, and you have some PCl4 plus and some PCl6 minus. Okay. What are the geometries of each one of these structures? Well, you have to draw the Lewis dot structure. Let me see if PCl5 is trigonal bipyramid. Right. So it's going to look like that. And it exceeds the octet, which phosphorus can do because it has access to 3D orbitals. Right. So that's the trigonal bipyramid. in the liquid and gaseous states. In the solid state, then we get the difference. Right, so PCl4 has 32 valence electrons, and if we draw the structure, then we get that tetrahedron with a positive charge. Don't forget the positive charge. Okay. If we look for the PCl5 minus or PCl6 minus, now we have 48 electrons. Just add them up. Right? 6 times 7 is 42, and phosphorus is 5, 47 plus 1 is 48. Right? We have to add 1 for the charge. And then we set them up in a regular arrangement and find now we've got an octahedron with a negative charge. All right. All right. I may have mentioned this in the past. Noble gases tend not to form compounds. Right? We don't find them in nature forming compounds. But the larger noble gases, argon, krypton, and xenon are better candidates because the bigger the atom, the easier it is to move electrons to different positions. And that way you can form bonds. Okay. If you force the situation, you can form bonds with these noble gases. Right? So we've got examples of krypton and xenon and radon compounds formed, and they usually form compounds easiest with halogens, their next door neighbors. Right. So in this case, this example, we have xenon tetrafluoride. Right? We know it's a compound. It has been isolated and identified. What we want to know is, does it have a dipole moment? Is it polar? Right? So we draw the structure. We draw the electronic structure first. Right, there it is. So xenon exceeds the octet. We should have been able to predict that, right? So it has 4 bonds, but it has 2 lone pairs on the xenon. Right? So that would be an octahedral, right? 6 groups around the xenon is an octahedral electronic geometry. Right? If we cover up those lone pairs, where are they going to be on that octahedron? Well, we said with 2 lone pairs, they're on the apexes. So that means all the fluorines are in that square planar. Well, we know that fluorine is more electronegative than xenon because of its position in the periodic table. So we should expect the polarity of the bonds to be toward the fluorine. Right? It's going to be that direction, in this direction, in this direction, and that direction. Okay? But notice, they're the same type of bond. Each one has the same type, and they're pointing to the corners of a square. They all got the same force, pointing in exactly symmetrical directions that cancel one another out. Right. But of course, researchers had to determine whether or not those lone pairs were on the square or they were on the apexes. And the polarity of the molecule helped them to decide which one was correct. Right? If they occur like this, like we know they do, then the molecule is nonpolar. If they occur on the square, that gives us a seesaw. And now the polarity of the bonds have a vector added sum, which would make the molecule polar. But the molecule is not polar. So that's how we decide between the two. In other words, B scenario is the correct one, and A scenario is wrong. And the bond angles are 90 degrees. Right? 90 degrees right here, right angles. Okay. Square planar molecule. I didn't talk about bond angles here. I probably should. This bond angle is going to be 180 degrees. Trigonal planar, of course, is going to be 120 degrees. That's the only possibility. Tetrahedral is 109.5 degrees with modifications for lone pairs. The seesaw, though, let's see, trigonal bipyramid. If we draw this structure like that, and like that, and like that, with our central atom here, then we have the possibility for, these are the bonds right here, there, there, there. So this was right angle. This is 180 degrees, and these are in a triangle, 120 degrees. So this one has the possibility of 120 degrees, 90 degrees, and 180 degrees. That's only if every position is occupied by an atom, right? If we remove an atom from this one, say from here, then you still have those possibilities because these two remain. And these two remain. So that doesn't change it much. But if we take that out, then we no longer have the possibility for 120 degrees if we've got two lone pairs. Right? Then we only have this one, this one, this one in a T. So it's either 180 or 90. Right? So there are your possibilities. The octahedral, like that, with a central atom. Now you have the possibility for here, 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 all the way around is 90 degrees, and here, here is 180 degrees, or here, here. So that's only 90 and 180 are the possibilities for octahedron. All right. So there's no dipole moment for this molecule because all of the polar bonds cancel each other out. In their dipole moments cancel. All right. Stop the share. We're done.